Welcome to Topic 5 in Define, Business Results for Projects. So let's talk about defects per unit. Now, defects per unit, or DPU, is the average number of defects per unit of the product. And it's calculated by taking the total number of our defects divided by the total number of our units. So let's do an example. So first we have to determine what our defects per unit is. And then we have to know how many units we have. So in the first example, let's say that we have 0 defects per unit, but we calculated 70 units. That's good. No defects. The next one is we had 1 defect out of 20 units, and then 2 defects out of 5. And then we had 3 out of 4, and then 5 out of 1. So now let's do our calculation. So it's really easy on how to do this. The first thing we have to do is set up our divisional line. So we have 1 times 20. We have 2 times 5 plus 2 times 5. And then we're going to have plus 3 times 4. And then we're going to have plus 5 times 1. Okay, so that's how we're going to start off with, right? So we can do each of these individual. Now the reason why 0 times 70 is there because that's not part of the deal, right? Because we're looking at down here now. So we have our defects, 1, 2, 3, 5, 1, 2, 3, 5, right? Multiplied by their particular amount of defects. And then we do it this way. 70 plus 20 plus 5 plus 4 plus 1. Right? Easy way to do it. So all of this comes to 47 divided by 100. Then we take the proportion, or the percentage of that, and it's 47%. So our defects per unit is 47%. So let's talk about throughput yield. Throughput yield, or TPY, is the number of acceptable pieces at the end of a process divided by the number of starting pieces, which is going to exclude any scrap and rework, meaning that scrap and rework are part of our calculation. Rework is a part of the TPY calculation. We use a process map as a guide for evaluating each individual process. Throughput yield is used to only measure a single process. Sometimes only raw material is available at the start, so it may be necessary to convert the raw material to any expected pieces that should make or use a unit of weight at the start and then weigh it out at the end to calculate a final yield, but that's a different story. The unit of measure when we calculate throughput yield should be the same for the numerator and denominator. So here I have an example. It's a really simple process map. It starts with process step 1, that moves to process step 2, that has some sort of decision-making diamond, and then it has process step 3. So we're going to figure throughput yield for each individual process step. So our process is going to begin with 50 pieces. So 50 pieces are going to enter into process step 1. Now let's say that out of those 50 pieces that are being processed, 4 of them are considered scrap, coming out of process step 1. 6 pieces have to be reworked. So in process step 1, come the exit, 4 are going to be total trash, 6 are going to be reworked. So we started with 50. So 50 is our denominator. We take 50 and we subtract our scrap and our rework, and that gives us 40. So out of all 50 pieces, 40 pieces came through process step 1 successfully with 0 defects. To find the throughput yield is a simple division. 40 divided by 50 is going to give us 80%. So our throughput yield for process step 1 is 80%. Now we have to say how many of these pieces are moving on to process step number 2, because we have to remember that each one of these process steps are mutually exclusive when we're talking about throughput yield. Well, we know that 40 make it through. However, 6 of which have to be reworked. So we know at this point our denominator then goes to 46. The 40 that made it through successfully the first time plus the 6 that had to be reworked gives us the 46. The 4 that were scrap are just trash. They're scrap. So let's say, just for example purposes, that in process step 2, none of these 46 were considered scrap. But 12 had to be reworked. So now how do we figure our throughput yield? Well, 46 went in and 12 had to be reworked. We have to subtract our 12 from our 46, which gives us 34. So 34 units or pieces went through process step number 2 without the need of scrap or rework. We do our calculation again, and it comes up to be like 73.9%. So in process step 1, we have a throughput yield of 80%. In process step 2, we have a throughput of 73.9%. So now we move on to process step number 3. The same thing applies. Well, we know that 34 made it through successfully the first time. 12 had to take a rework or be done a second time. So we add 34 plus 12, and that gives us the same number of 46. So our denominator stays 46. But let's say in process step 3 that 9 of those pieces had to be considered scrap. So they didn't even make it through the process. They're considered defective. And then we have 0 in rework. So let's calculate our throughput yield for process step number 3. We take our 46, we subtract our 9, because that's all we have, and that's going to give us 37. So 37 pieces come out of process step number 3 without a defect. We do our math. 37 divided by 46 is 80 and some change, 80.4%. Yep, that's right. So 80.4% is our throughput yield for only process step number 3. So when we look at a process from a step-by-step perspective, step number 1 gives us an 80% throughput yield, but step number 2 gives us 73.9. Step number 3 brings us a little bit closer to 80.4. And so the questions that we have to ask here is, what's going on with all the rework? Why in process step 2 are we needing to rework more units? Because that's significantly decreasing our throughput yield. And that's how you calculate throughput yield. So another calculation that we use in Six Sigma is something called rolled throughput yield. And rolled throughput yield is the probability that a process with more than one step will produce a defect-free unit. It is the product of yields for each process step of the entire process. So for any process, it is ideal for that a process to produce its product without defects and without rework. Rolled throughput yield quantifies the accumulative effects of inefficiencies found throughout the process, and it's typically one of the key calculations that we use in Six Sigma. So rolled throughput yield is calculated by multiplying the yields of each process step. Now, calculations can become increasingly complicated as more parallel processes are introduced. And it's first necessary to calculate the yield of each process step. So now going back to the example that we did for throughput yield, these were the percentages of each individual process step. And I translated them to decimals for easier mathematics. So in process step 1, we had a throughput yield of 80%. In process step 2, we had a throughput yield of 73.9%. And in process step 3, we had a throughput yield of 80.4%. So that means that we started with 50 pieces that went into process step 1, and only 37 of those 50 pieces came out of the process successfully. So to calculate rolled throughput yield, we multiply the throughput yield of each individual process step. So the first thing that we do is we're going to multiply 0.80, which is 80%, to 0.739, or 73.9%. And when we calculate that out, we're going to get 16.6%. That is the product of both of these numbers. Then what we're going to do is have to take the product of 80.4 to our 16.6, which gives us 28.10%, so 28.1%. So our rolled throughput yield of this three-step process is equal to 28.10%. And that's how you calculate rolled throughput yield. So let's do another example of first pass yield, or throughput yield, and rolled throughput yield. So again, let's just do a three-step process. And let's say that we're going to start this time with 100 units or pieces going into process step 1. So in process step 1, 100 pieces goes in. Let's say that 10 of those pieces are considered scrap and 5 of those pieces are considered rework. So how do we calculate our first pass yield, or our throughput yield, for process step 1? Well, we know that 100 went in, so that's our denominator. And how many came out? Well, 100 minus 10 is 90, minus 5 is 85. So 85 pieces came through successfully, or 85%. So we're just going to do 85. So then, since each one of these are mutually exclusive of each other, how many pieces then go into process step number 2? Well, the 85 are going to go in because they successfully passed. And then the 5 that we reworked will go into process step 2. So 85 plus 5 is equal to 90. So now let's say out of those 90, 5 of them are considered scrap. And 5 of them need to be reworked. What is our throughput yield, or our first pass yield, for process step number 2? Well, 90 minus 5 is 85, minus another 5 is 80. So it's 80. So when we calculate 80 divided by 90 into a decimal, it comes up to 88.9%. Or here, we'll do it this way, 0.889. So then what's going to be our throughput for the next one? Well, we know that 80 went through successfully, and 5 had to be reworked. So our denominator becomes 85. Now let's just say, for example purposes, that there were no scrap pieces. And also, none of them had to be reworked. So our throughput yield is 85. So out of 100 pieces that start in process step 1, 85 of them make it to the end. 85 divided by itself is 1, or 100%. So now to calculate our rolled throughput yield, we just take 85, we multiply that by 85%, multiply that by 88.9%, multiply that by 100%, and we get 75%. So our rolled throughput yield for this process is 75%. Now, defects per million opportunities, or DPMO, is a measure of process performance. It standardizes the number of defects at the opportunity level and allows comparison of the processes with different complexities. So to calculate DPMO, what we're going to do is we're going to take our total number of defects divided by the total number of opportunities. So total number of defects divided by the total number of opportunities to create them. And then we're going to multiply that by 1 million. Or, depending if you use scientific notation, it's 10 to the 6. So let's say that we have 5 units, and each one of those units have 5 defects or 5 opportunities for defects. So how many defects are we going to have? Well, let's say that we have 8 defects. So what's our total number of defects? Well, our total number of defects is 8. Now, to find the total amount of opportunities, remember that we have 5 units, each with 5 opportunities to create a defect. So 5 times 5 is 25. So it's 8 divided by 25. So it's the total number of our defects divided by the total number of our opportunities. And then we're going to multiply that to 1 million. And that's going to come to the number of 320,000. So our defects per million opportunities is 320,000. The cost of quality. The cost of quality, or COQ, is the cost incurred by a process because it cannot consistently make a perfect product. Now, there are 4 types of COQ. The first one is preventative cost. This is where cost is incurred in preventing a failure. Then we have appraisal cost. This is where cost is incurred to test a product for quality conformance. Then we have internal failure cost. This is where the cost is associated with defects that are identified before a product reaches the customer. And then finally, we have the external failure cost, which is the cost that's associated with defects after a product reaches the customer.